If you have a moment, consider watching in full screen. Let the room dim slightly around you. If this journey through the cold reaches of the outer solar system and beyond resonates with you, the subscribe button waits quietly at the edge of the frame. No urgency, no pressure, just an invitation to return when the next story unfolds. Now let us begin. In the autumn of 2017, a telescope on the island of Maui turned its aperture toward a region of sky that had, moments before, been unremarkable. The Pan-STARRS 1 telescope, designed to survey the heavens for near-Earth objects, asteroids, and comets that might pose a threat or simply pass unnoticed through the solar neighborhood, captured light from something moving. This was not unusual. The telescope captures thousands of moving points of light each night. But this object, later designated 1I/2017 U1 and subsequently named ʻOumuamua, was moving in a way that did not fit the expected patterns. Its velocity relative to the Sun, its trajectory, and the hyperbolic shape of its orbit suggested that it had not originated within the gravitational architecture of our solar system. It had come from somewhere else. It was interstellar. The term interstellar carries with it a weight that exceeds its technical definition. In the vocabulary of astronomy, interstellar simply means existing or occurring between stars. But in the context of an object passing through our solar system, it implies a journey of incomprehensible duration, a passage through the vast empty spaces that separate stellar systems, a solitary traverse across light years without the warmth of a parent star, without the gravitational anchor of a planetary system, adrift in the galactic medium for millions or tens of millions of years. When ʻOumuamua was identified, it became the first object ever confirmed to have traveled to us from interstellar space. Not the first suspected, not the first hypothesized, the first confirmed. And its arrival marked the beginning of a new chapter in observational astronomy, one in which humanity could no longer regard the solar system as an isolated island, but rather as a region of space occasionally visited by wanderers from elsewhere. Before ʻOumuamua, astronomers understood theoretically that interstellar objects should exist. Planetary system formation models, simulations of gravitational interactions during the chaotic early epochs of stellar system assembly, and the dynamics of galactic structure all pointed toward the inevitable conclusion that countless objects must be ejected from their birth systems and sent wandering through the galaxy. When planets form around a young star, the protoplanetary disk from which they coalesce is a turbulent environment. Gas and dust spiral inward, clump together, grow into planetesimals, and eventually into planets. But not all material makes it into stable orbits. Gravitational interactions between forming planets, close encounters with massive bodies, and the influence of the central star itself can fling smaller objects outward beyond the escape velocity of the system into interstellar space. These ejected bodies become rogue planets, free-floating planetesimals, or interstellar asteroids and comets, depending on their size and composition. Our own solar system almost certainly contributed to this population. Jupiter, with its immense gravitational influence, likely scattered countless objects outward during its migration through the early solar system. Some of those objects remain in the distant Oort cloud, a vast spherical shell of icy bodies surrounding the Sun at distances of tens of thousands of astronomical units. Others were ejected entirely, sent into the galaxy to drift indefinitely. If our solar system ejected material, then so too must every other planetary system. The Milky Way galaxy contains hundreds of billions of stars, and current estimates suggest that a substantial fraction of those stars host planetary systems. Even if only a small percentage of the material in each system is ejected, the cumulative population of interstellar objects in a galaxy must be enormous. Estimates vary, but some models suggest that at any given moment, there are trillions upon trillions of interstellar objects traveling through the Milky Way, most of them small, most of them dark, most of them undetectable. They pass through the solar system regularly, perhaps several per year, but they are faint and fast-moving, and until recently, we lack the observational tools to detect them. Oumuamua was not the first interstellar object to pass through the solar system. It was simply the first we noticed. Detection of such an object requires a combination of survey capability, timing, and fortune. The object must pass close enough to the sun to reflect sufficient sunlight to be detected by ground-based telescopes. It must be observed at the right time, before it fades back into the darkness beyond the solar system. And it must be recognized as unusual, its trajectory flagged as non-solar system in origin, which requires precise astrometric measurements and rapid follow-up observations. Pan-STARRS 1, with its wide-field imaging capability and automated survey protocols, was well suited to this task. The telescope is located atop Haleakala, a dormant volcano on Maui, at an altitude that places it above much of the atmospheric turbulence that degrades astronomical observations. Each night, it sweeps the sky, capturing images of vast regions and comparing them to previous images to identify anything that has moved or changed. The software that processes these images is designed to flag moving objects, calculate their orbits, and determine whether they pose any threat to Earth. On October 19, 2017, the system flagged an object that had been captured in images taken the previous night. Initial orbital calculations suggested it was an asteroid or comet, but as more observations came in over the following days, it became clear that the object was not bound to the sun. Its orbit was hyperbolic, not elliptical, meaning it was moving too fast to be captured by the sun's gravity. It had come from interstellar space and would return to interstellar space. The name ʻOumuamua is Hawaiian, chosen in recognition of the telescope's location. It translates roughly to scout or messenger, a reference to the object's role as an emissary from another part of the galaxy. The name carries a sense of arrival, of something sent ahead to announce or explore. Within days of its detection, astronomers around the world redirected their telescopes toward ʻOumuamua, racing to gather as much data as possible before it moved too far from the sun and became too faint to observe. This observational window was brief. ʻOumuamua was already outbound, receding from the inner solar system at high speed, and within a matter of weeks, it would be beyond the reach of even the most powerful telescopes. Every spectrum, every photometric measurement, every astrometric data point was critical. The object would not return. There would be no second chance to study it. The first task was to determine its trajectory with precision. By tracking the object's position over time and measuring its velocity, astronomers could reconstruct its orbit and determine where it had come from and where it was going. This involves solving the equations of celestial mechanics, which describe how objects move under the influence of gravity. In a two-body problem, where only the sun and the object are considered, the mathematics are straightforward and the orbit is a conic section, an ellipse, parabola, or hyperbola, depending on the object's energy. ʻOumuamua's orbit was clearly hyperbolic, indicating that its kinetic energy exceeded the gravitational binding energy of the sun. But determining the precise shape and orientation of the orbit required accounting for the gravitational influence of the planets, particularly Jupiter, as well as non-gravitational forces such as radiation pressure and outgassing, if the object were a comet. Astrometric observations, which measure the object's position on the sky with subarcsecond precision, were combined with radial velocity measurements, which use the Doppler shift of spectral lines to determine how fast the object is moving toward or away from the observer. These data were fed into orbit determination algorithms, which iteratively refine the orbital parameters to produce the best fit to the observations. The resulting orbit revealed several key facts. First, ʻOumuamua had entered the solar system from the direction of the constellation Lyra, approaching from above the plane of the solar system at a relatively shallow angle. Its velocity at infinity, the speed it would have far from the sun's gravitational influence, was approximately 26 kilometers per second relative to the local standard of rest, which is the average motion of stars in the sun's neighborhood of the galaxy. This velocity is consistent with the typical velocities of stars in the solar neighborhood, suggesting that ʻOumuamua had not been accelerated by any recent close encounter with another star or massive object. It was simply drifting through the galaxy at the ambient velocity of the stellar population. Second, the object had made its closest approach to the sun on September 9th, 2017, passing within approximately 0.25 astronomical units, roughly a quarter of the Earth-Sun distance, well inside the orbit of Mercury. At this distance, the Sun's heat would have been intense, and if Oumuamua had contained significant amounts of volatile ices, such as water, carbon dioxide, or carbon monoxide, those ices should have sublimated, producing a visible coma and tail characteristic of a comet. But no such coma or tail was observed. Oumuamua appeared inactive, asteroid-like in its lack of cometary features, despite having passed so close to the Sun. Photometric observations, which measure the brightness of the object over time, provided another layer of mystery. Oumuamua's brightness varied dramatically and periodically, with changes of up to a factor of 10 over a period of approximately 7.3 hours. In the context of asteroids, brightness variations are typically caused by rotation. As a non-spherical object rotates, it presents different cross-sectional areas to the observer, causing its brightness to vary. The amplitude of the variation is related to the object's shape. A spherical object shows no variation, while a highly elongated object shows large variations. The tenfold brightness variation of Oumuamua implied an extreme elongation, with an axis ratio of at least 10:1, meaning it was at least 10 times longer than it was wide. This is far more elongated than any known asteroid or comet in the solar system. Most asteroids are irregular and lumpy, but even the most elongated ones have axis ratios of only 3 or 4:1. Oumuamua appear to be shaped like a cigar or a pancake, either a long needle-like object or a flat disk, though distinguishing between these two possibilities from photometric data alone is difficult. Spectroscopic observations, which analyze the light reflected from the object to determine its surface composition, were more challenging. Oumuamua was faint, and obtaining a high-quality spectrum required large telescopes and long integration times. The spectra that were obtained showed a reddish color, similar to the surfaces of many outer solar system objects, such as Kuiper Belt objects and the surfaces of some comets. This reddish coloration is typically attributed to organic compounds that have been irradiated by cosmic rays over long timescales, a process known as space weathering. The presence of such a color suggests that Oumuamua had been exposed to the interstellar medium for an extended period, possibly millions of years, during which cosmic ray bombardment had altered the chemistry of its surface. However, the spectra did not reveal any strong absorption features that would indicate the presence of specific minerals or ices. The surface appeared relatively featureless, which could be due to the low signal-to-noise ratio of the observations or to the fact that the surface composition was genuinely homogeneous and composed of materials that do not produce strong spectral features in the visible and near-infrared wavelengths where the observations were made. As the observational campaign continued, another puzzling feature emerged. When astronomers attempted to refine the orbital parameters using the growing set of astrometric observations, they found that the orbit could not be fit perfectly by a purely gravitational model. There was a small but statistically significant deviation from the expected trajectory, a slight acceleration in the direction away from the Sun. This acceleration was first noticed by researchers analyzing the astrometric data several months after Oumuamua had faded from view, and it sparked intense debate. In comets, such an acceleration is well understood and attributed to outgassing. When a comet approaches the Sun, volatile ices on its surface and in its interior sublimate, ejecting gas and dust into space. This outgassing acts like a weak rocket engine, producing a force that can accelerate the comet. The direction and magnitude of the acceleration depend on the distribution of active areas on the comet's surface and the rotation state of the nucleus. But Oumuamua had shown no signs of cometary activity. No coma, no tail, no excess emission in infrared wavelengths that would indicate the presence of warm dust. If outgassing was responsible for the acceleration, it had to be of a type that produced no detectable dust or gas emission, which is unusual. Several hypotheses were proposed to explain the acceleration. One possibility was that Oumuamua was indeed a comet, but that its activity was producing only gas, not dust, and that the gas was composed of molecules that do not emit strongly in the wavelengths where observations were made. Molecular hydrogen or nitrogen, for example, would be difficult to detect. Another possibility was that the acceleration was caused by radiation pressure, the force exerted by sunlight on the object's surface. Radiation pressure is always present, but its effect is typically small unless the object is very lightweight for its size. For radiation pressure to produce the observed acceleration, ʻOumuamua would need to have an extremely low density, far lower than typical rock or ice. This led some researchers to propose that ʻOumuamua might be a fractal aggregate, a porous structure with very little solid material, or even a thin sheet, like a sail, which would have a large surface area relative to its mass. This sail-like hypothesis was further developed by some to suggest that ʻOumuamua could be a piece of artificial technology, a light sail from an extraterrestrial civilization. Though this idea was met with skepticism by most of the scientific community due to the lack of any other evidence for artificial origin and the existence of more mundane explanations. The debate over ʻOumuamua's nature and the cause of its acceleration was still ongoing when, in August 2019, another interstellar object was detected. This time, the discovery was made by Borisov, an amateur astronomer operating a telescope at the Margo Observatory in Crimea. The object, initially designated C/2019 Q4 and later renamed 2I/Borisov to acknowledge its interstellar origin, was immediately recognized as unusual due to its hyperbolic orbit. Unlike ʻOumuamua, however, 2I/Borisov displayed clear cometary activity from the moment of its discovery. It had a distinct coma and a faint tail, and spectroscopic observations quickly confirmed the presence of gas emission, including lines from cyanide and diatomic carbon, molecules commonly found in comets within our solar system. The discovery of 2I/Borisov was significant not only because it was the second confirmed interstellar object, but also because it provided a comparison point to ʻOumuamua. Where ʻOumuamua had been mysterious and anomalous, 2I/Borisov appeared to be a relatively normal comet, just one that happened to have been ejected from another planetary system. The trajectory of 2I/Borisov was similar to that of ʻOumuamua in that it was hyperbolic, indicating an interstellar origin, but the details differed. 2I/Borisov approached the solar system from a different direction, and its velocity at infinity was approximately 32 kilometers per second, somewhat higher than ʻOumuamua's, but still consistent with the typical velocities of stars in the galactic neighborhood. The object's perihelion, its closest approach to the Sun, occurred on December 8, 2019, at a distance of approximately 2 astronomical units, twice the Earth-Sun distance, well outside the orbit of Mars. This meant that 2I/Borisov did not experience the intense solar heating that ʻOumuamua had, but it was still close enough for significant cometary activity to occur. The detection of 2I/Borisov several months before perihelion gave astronomers a much longer observational window than they had with ʻOumuamua. They could plan observation campaigns, coordinate telescope time, and study the object in detail as it approached past perihelion and then receded back into interstellar space. Photometric observations of 2I/Borisov revealed a much less extreme shape than ʻOumuamua. The brightness variations were smaller, suggesting that the nucleus was more spherical or at least less elongated. The size of a nucleus was estimated to be roughly 1 kilometer in diameter, similar to many small comets in the solar system. Spectroscopic observations were more fruitful than they had been for ʻOumuamua, thanks to the longer observational window and the presence of gas emission. Astronomers detected emission lines from a variety of molecules, including CN, C2, OH, and NH2, all of which are common cometary molecules and are produced by the photodissociation of parent molecules, such as HCN, C2H2, H2O, and NH3. The ratios of these molecules were compared to those observed in solar system comets, and the results were striking. The composition of 2I/Borisov was remarkably similar to that of comets from the Oort cloud, the distant reservoir of icy bodies that surrounds the solar system. This similarity suggested that the formation conditions in the planetary system from which 2I/Borisov was ejected were not dramatically different from those in our own solar system. One particularly interesting result from the spectroscopic observations of 2I/Borisov was the detection of gaseous nickel and iron in its coma. This detection was surprising because, while metals are abundant in comets, they're typically locked up in solid dust grains and are not present in significant quantities in the gas phase. The presence of gaseous metals suggests that the dust grains in 2I/Borisov were being heated to high temperatures, possibly by the sublimation of very volatile ices or by some other process that released metals from the dust. This finding raised questions about the thermal structure and composition of the comet's interior and highlighted the value of studying interstellar comets as a window into the processes that occur in other planetary systems. Polarimetric observations, which measure the polarization state of light reflected from the object, provided additional constraints on the properties of the dust in 2I/Borisov's coma. Polarization is sensitive to the size, shape, and composition of dust particles, and the polarization of light from 2I/Borisov was found to be similar to that of solar system comets, further supporting the conclusion that 2I/Borisov was not fundamentally different from comets formed in the solar system. However, there were subtle differences that hinted at variations in dust properties, possibly reflecting differences in the formation environment or the thermal history of the comet. The study of 2I/Borisov also included observations at longer wavelengths, in the millimeter and submillimeter range, using radio telescopes. These observations are sensitive to the emission from dust and gas at larger distances from the nucleus, where the material has had time to cool and expand. The millimeter observations of 2I/Borisov detected emission from carbon monoxide, CO, which is a common and relatively abundant molecule in comets. The detection of CO allowed astronomers to estimate the production rate of gas from the nucleus and to constrain the composition of the ices in the comet's interior. The CO production rate was found to be relatively high compared to the production rate of water, which is the dominant volatile in most solar system comets. This suggested that 2I/Borisov might have formed in a colder region of its parent planetary system, where CO ice could condense and be retained, or that it had experienced less thermal processing than typical solar system comets. As with ʻOumuamua, the orbit of 2I/Borisov was carefully monitored to look for any non-gravitational accelerations. Unlike ʻOumuamua, the acceleration observed in 2I/Borisov was consistent with standard cometary outgassing. The magnitude and direction of the acceleration could be explained by the sublimation of water ice and other volatiles, producing a rocket-like force that nudged the comet's trajectory. This behavior was expected for an active comet and did not raise the same questions that the acceleration of ʻOumuamua had. The fact that 2I/Borisov behaved like a normal comet, while ʻOumuamua did not further deepen the mystery surrounding ʻOumuamua. It suggested that interstellar objects might come in a variety of types, some comet-like, some asteroid-like, and some perhaps unlike anything seen in the solar system. The third interstellar object, designated 3I/Atlas, was detected in 2021, though its status as an interstellar object was initially uncertain and remains a subject of ongoing investigation. The object was discovered by the Asteroid Terrestrial Impact Last Alert System, ATLAS, a network of telescopes designed to detect potentially hazardous asteroids. The initial orbital calculations suggested that 3I/Atlas might have an orbit that was weakly bound to the Sun, meaning it could be a very long-period comet from the Oort cloud rather than a truly interstellar object. However, as more observations were gathered, the orbit appeared to be more consistent with a hyperbolic trajectory, indicating an interstellar origin. The uncertainty in the orbit determination was larger than for ʻOumuamua or 2I/Borisov, partly because 3I/Atlas was fainter and more difficult to observe, and partly because it was discovered later in its passage through the solar system, leaving less time for follow-up observations before it faded from view. The designation 3I, meaning the third interstellar object, was assigned provisionally, pending confirmation that the orbit was indeed hyperbolic and not an extremely elongated ellipse. This distinction is important because the difference between a very elongated ellipse and a hyperbola can be small, and the orbital energy, which determines whether the orbit is bound or unbound, depends on precise measurements of the object's position and velocity. Small errors in the observations can lead to uncertainty in the orbital parameters, and distinguishing between a comet with an orbital period of thousands of years and a truly interstellar object can be challenging. In the case of 3I/Atlas, the available data suggested that the orbit was hyperbolic, but the eccentricity, the parameter that describes the shape of the orbit, was close to 1, meaning the orbit was only slightly unbound. This made the determination less certain than for ʻOumuamua or 2I/Borisov, where the eccentricities were clearly greater than 1 and the interstellar nature of the objects was unambiguous. Observations of 3I/Atlas were limited by its faintness and the short observational window. The object did not display obvious cometary activity in the initial observations, but this does not necessarily mean it was inactive, as the sensitivity of the observations may not have been sufficient to detect a weak coma or tail. Spectroscopic observations, which could have provided information about the surface composition or gas emission, were not obtained due to the object's faintness and the limited availability of large telescopes during the observational window. As a result, much less is known about 3I/Atlas than about ʻOumuamua or 2I/Borisov. The object remains an intriguing but poorly characterized member of the small catalog of confirmed or suspected interstellar objects. The detection of 3 interstellar objects in the span of a few years has transformed the field of interstellar object studies from a theoretical curiosity to an active area of observational research. Before 2017, no interstellar objects had been confirmed, and the study of such objects was limited to speculation and modeling. Now, astronomers have real data, real trajectories, and real physical properties to work with. This has allowed them to begin testing the predictions of planetary system formation models, to constrain the population of interstellar objects in the galaxy, and to develop strategies for detecting and studying future interstellar visitors. The detection rate of interstellar objects provides information about their number density in the galaxy. If we assume that the objects detected so far are representative of the population as a whole, and that they're distributed uniformly throughout the galaxy, then we can use the detection rate to estimate how many such objects exist. The calculation involves several factors, including the survey capabilities of the telescopes used to detect the objects, the geometric probability that an object will pass close enough to the Sun to be detected, and the typical velocity of interstellar objects. The result of such calculations suggests that there are likely millions or billions of interstellar objects larger than a few tens of meters within the solar system's vicinity at any given time, though most of them are too faint or too far away to be detected with current technology. Smaller objects, those less than a few tens of meters in size, will be even more numerous but even harder to detect. The population of interstellar objects is probably dominated by small bodies, just as the population of asteroids and comets in the solar system is dominated by small bodies. The origin of interstellar objects is tied to the process of planetary system formation and the subsequent dynamical evolution of those systems. When a planetary system forms, the protoplanetary disk contains far more material than eventually ends up in planets. Most of the solid material is in the form of small particles, dust, and pebbles, which gradually accumulate into larger bodies through collisions and gravitational attraction. This process is not perfectly efficient, and many small bodies remain scattered throughout the disk even after the planets have formed. These leftover bodies, known as planetesimals, can be perturbed by the gravitational influence of the planets, particularly the giant planets, which have the strongest gravitational fields. Perturbations can send planetesimals onto new orbits, some of which intersect with other planets, leading to collisions or further perturbations, and some of which carry the planetesimals to large distances from the central star, where they may remain in a loosely bound reservoir like the Oort cloud. In some cases, the perturbations are strong enough to accelerate the planetesimal beyond the escape velocity of the system, ejecting it into interstellar space. The efficiency of this ejection process depends on the architecture of the planetary system. Systems with multiple giant planets, or systems where planets migrate inward or outward over time, are more likely to experience strong dynamical interactions that lead to ejections. Our own solar system underwent significant dynamical upheaval in its early history, a period sometimes referred to as the era of late heavy bombardment, during which the giant planets are thought to have migrated and scattered large numbers of planetesimals. Jupiter, in particular, is thought to have played a major role in ejecting objects from a solar system. The gravitational slingshot effect, in which a small body passes close to a massive planet and gains energy from the encounter, can accelerate objects to very high velocities, sufficient to escape the sun's gravity. Similar processes occur in other planetary systems, and the diversity of planetary system architectures observed around other stars suggests that the rate and nature of ejections vary from system to system. The composition of ejected objects depends on where they formed in the protoplanetary disk. Objects that formed close to the central star, in the warm inner regions of the disk, are likely to be rocky or metallic, composed of refractory materials that can withstand high temperatures. Objects that formed farther out, beyond the snow line, the distance from the star where water ice can condense, are likely to be icy, containing water, carbon dioxide, methane, and other volatile compounds. The snow line is not a sharp boundary, but rather a region where the temperature drops below the condensation temperature of water, and its location depends on the luminosity of the star and the density of the disk. In the solar system, the snow line is thought to have been located somewhere between the orbits of Mars and Jupiter during the early stages of planet formation. Objects that formed beyond the snow line, such as comets, are rich in ices, while objects that formed inside the snow line, such as asteroids, are rocky. When objects are ejected from a planetary system, they carry with them a record of the conditions in the region where they formed. Studying the composition of interstellar objects can therefore provide insights into the structure and chemistry of their parent protoplanetary disks. The case of Oumuamua is particularly interesting in this regard because its lack of cometary activity suggests that it either formed in the inner, rocky region of its parent system, or that it lost its volatile ices over time due to thermal processing or cosmic ray irradiation. The extreme elongation of Oumuamua, if real, also raises questions about how such an object could form. In the solar system, elongated asteroids are thought to result from collisions that break apart larger bodies or from tidal forces that stretch objects during close encounters with planets. It is possible that Oumuamua is a fragment from a larger body that was shattered in a collision, either in its parent system or during its journey through interstellar space, though collisions in interstellar space are extremely rare due to the vast distances between objects. Another possibility is that Oumuamua is not as elongated as the photometric data suggest, and that the brightness variations are caused by some other mechanism, such as surface albedo variations or a complex rotation state. Distinguishing between these possibilities would require more detailed observations, which are no longer possible for Oumuamua, but similar observations could be made of future interstellar objects if they are detected early enough. The composition of Borisov, on the other hand, is more clearly comet-like, suggesting that it formed in the outer regions of its parent system beyond the snow line. The similarity of its composition to that of Oort cloud comets in the solar system suggests that the processes that form and preserve icy bodies are similar across different planetary systems. This is somewhat reassuring from the perspective of comparative planetary science, as it suggests that the solar system is not unique in its properties and that the lessons learned from studying solar system objects can be applied to objects from other systems. However, the detailed composition of Borisov, particularly the high abundance of carbon monoxide, suggests that there may be subtle differences in the formation conditions or thermal histories of comets in different systems. These differences could reflect variations in the temperature and density profiles of protoplanetary disks, the timing of planet formation, or the dynamical evolution of the system after planet formation. The study of interstellar objects also intersects with the field of astrobiology, the study of the origin, evolution, distribution, and future of life in the universe. One of the key questions in astrobiology is whether the building blocks of life, such as organic molecules and water, are common throughout the galaxy, and whether these building blocks can be transported between planetary systems. Comets are known to contain a rich inventory of organic molecules, including amino acids, the building blocks of proteins, and it is thought that comets may have played a role in delivering organic material and water to the early Earth, thereby contributing to the origin of life. If comets from other planetary systems also contain organic molecules, then interstellar comets could potentially transport these molecules between systems, seeding planets in one system with material from another. This idea, known as panspermia or more specifically lithopanspermia, when solid objects are involved, is speculative and controversial, but the discovery of interstellar comets like ʻOumuamua/Borisov makes it a testable hypothesis. By studying the composition of interstellar comets in detail, astronomers can determine whether they contain the same kinds of organic molecules found in solar system comets, and whether these molecules are in a form that could survive the long journey through interstellar space and contribute to the chemistry of a new planetary system. The detection and characterization of interstellar objects rely on a combination of observational techniques, each of which provides different kinds of information. Astrometry, the precise measurement of the positions of celestial objects, is essential for determining orbits and identifying objects with hyperbolic trajectories. Photometry, the measurement of brightness, provides information about the size, shape, and rotation of objects. Spectroscopy, the analysis of light at different wavelengths, reveals the composition of the object's surface or, in the case of active comets, the gases in the coma. Polarimetry, the measurement of the polarization state of light, provides information about the properties of dust particles. Thermal infrared observations measure the heat emitted by the object, which depends on its size, albedo, and surface temperature. Radio observations can detect emission from molecules in the gas phase, providing additional compositional information. Each of these techniques has its own strengths and limitations, and a comprehensive understanding of an interstellar object requires combining data from multiple techniques. The observational challenges associated with interstellar objects are significant. These objects are typically faint because they are small and far from the sun, and they're moving rapidly, which means they fade quickly as they recede from the inner solar system. The observational window, the period of time during which the object is bright enough to be studied in detail, is often only a few weeks or months. This requires rapid response from the astronomical community, with observers coordinating to obtain as much data as possible before the object becomes too faint. The need for rapid response has led to the development of systems like the Minor Planet Center, which collects and disseminates observations of asteroids, comets, and other small bodies, and the Transit Name Server, which coordinates the designation of newly discovered transient objects. These systems allow astronomers around the world to quickly learn about new discoveries and contribute observations, maximizing the scientific return from each object. The future of interstellar object studies depends on the development of more powerful survey telescopes that can detect fainter and more distant objects. Several such telescopes are currently under construction or in the planning stages. The Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, or LSST, is a wide-field survey telescope located in Chile that is expected to begin operations in the mid-2020s. The Rubin Observatory will survey the entire visible sky every few nights, detecting millions of transient and moving objects, including a significant number of interstellar objects. Estimates suggest that the Rubin Observatory could detect one or more interstellar objects per year, and possibly as many as several per year, depending on the actual population density of such objects in the solar neighborhood. The increased detection rate will allow astronomers to build up a statistical sample of interstellar objects, studying their properties in aggregate, and searching for patterns or correlations that could reveal information about their origins and the diversity of planetary systems in the galaxy. In addition to ground-based surveys, space-based missions offer the possibility of more detailed studies of interstellar objects. A spacecraft mission to an interstellar object would be extremely challenging, given the high velocities involved and the short notice with which such objects are typically detected. However, several mission concepts have been proposed. One approach would be to use a fast-response mission, with a spacecraft on standby that could be launched on short notice when an interstellar object is detected. The spacecraft would need to be capable of achieving very high velocities, possibly through the use of solar sails or advanced propulsion systems, in order to catch up with the object before it leaves the solar system. Another approach would be to position a spacecraft in a distant orbit, such as in the outer solar system, where it could potentially intercept an interstellar object with less demanding propulsion requirements. Such missions would provide the opportunity to study an interstellar object up close, obtaining high-resolution images, detailed compositional measurements, and possibly even returning a sample to Earth. The non-gravitational acceleration of Oumuamua remains one of the most debated aspects of interstellar object studies. The acceleration was detected through careful analysis of the astrometric data, which showed that the object's trajectory deviated slightly from what would be expected based on gravitational forces alone. The magnitude of the acceleration was small, corresponding to a change in velocity of a few centimeters per second per day, but it was statistically significant and could not be explained by observational errors or by the gravitational effects of the planets or other solar system bodies. The direction of the acceleration was approximately radial, pointing away from the Sun, which is the direction expected for a force caused by outgassing or radiation pressure. However, as mentioned earlier, no cometary activity was detected, and this absence of activity has led to a range of explanations, some conventional and some more exotic. The most straightforward explanation for the acceleration is that it was caused by outgassing, but that the outgassing was producing a gas that is difficult to detect. Water vapor, the most common volatile in comets, produces a strong signal in infrared wavelengths, and the absence of such a signal places strong constraints on the rate of water production. However, other volatiles, such as molecular nitrogen or molecular hydrogen, do not produce strong infrared signals and could be outgassing without being detected. Molecular nitrogen, in particular, has been proposed as a candidate because it is known to be a major component of some icy bodies in the solar system, such as Pluto and Triton, and because it would sublime at relatively low temperatures, allowing outgassing to continue even as the object moved away from the Sun. Calculations have shown that outgassing of molecular nitrogen at a relatively modest rate could produce the observed acceleration without generating a detectable coma. This explanation requires that Oumuamua have a surface layer of nitrogen ice, which would be unusual but not impossible. Nitrogen ice is thought to be rare in the solar system because nitrogen is a relatively volatile element and tends to escape from small bodies, but in a different planetary system with different formation conditions, nitrogen ice might be more common. Another explanation for the acceleration is that it was caused by the sublimation of another volatile, such as solid hydrogen or solid carbon monoxide. Solid hydrogen would be extremely cold and would sublimate at very large distances from the Sun, where temperatures are only a few tens of degrees above absolute zero. If Oumuamua had a surface layer of solid hydrogen, it could have been outgassing hydrogen molecules as it passed through the solar system, and this outgassing would be very difficult to detect because molecular hydrogen does not emit strongly at any wavelength. However, the formation and preservation of solid hydrogen on an interstellar object is problematic, as hydrogen is the lightest element and would tend to escape from a small body's gravity, and because solid hydrogen is only stable at extremely low temperatures, which would require that the object had never been exposed to significant heating, even during its formation. Radiation pressure, the force exerted by sunlight, is another potential cause of the acceleration. Radiation pressure is always present when an object is illuminated by the sun, and it acts to push the object away from the sun. The force depends on the object's cross-sectional area and its mass. For typical rocky or icy bodies, radiation pressure is negligible compared to gravitational forces, but for objects with very low bulk densities or very high surface area to mass ratios, radiation pressure can be significant. If Oumuamua were a thin sheet or a highly porous fractal aggregate, with a density much lower than solid rock or ice, then radiation pressure could produce the observed acceleration. This possibility has been explored in detail by several research groups, with some proposing that Oumuamua might be a fragment of a larger body that was disrupted by tidal forces or a collision, producing a thin flake, or that it might be a fluffy aggregate of dust particles held together by weak forces. However, such objects would be mechanically fragile and might not survive the stresses of passing close to the sun or the thermal and radiation environment of interstellar space. The formation mechanism for such an object is also unclear, as there are no known analogs in the solar system. The most controversial explanation for the acceleration is that Oumuamua is not a natural object at all, but rather a piece of technology, specifically a light sail, a thin reflective sheet used to propel a spacecraft using radiation pressure. This hypothesis was put forward by some researchers based on the fact that the acceleration could be explained by radiation pressure if Oumuamua had a low density and a high reflectivity, properties that would be consistent with a light sail. The hypothesis was further motivated by the lack of any other obvious explanation for the acceleration and by the fact that light sails are a theoretically plausible form of interstellar propulsion for advanced civilizations. However, the hypothesis has been met with considerable skepticism for several reasons. First, there is no other evidence for artificial origin. The object does not emit any signals in radio or other wavelengths. It does not have any obvious structural features that would suggest technology, and its trajectory does not appear to be under control, as would be expected for a functioning spacecraft. Second, the hypothesis relies on a number of ad hoc assumptions, such as the idea that the light sail is tumbling, which would explain the brightness variations, and that it is non-functional, which would explain the lack of signals or course corrections. Third, there are natural explanations for the acceleration that, while not conclusive, are more parsimonious and do not require invoking extraterrestrial intelligence. The scientific consensus is that Oumuamua is most likely a natural object, either an asteroid or a comet, and that the acceleration is due to outgassing or some other natural process. But the debate continues and will likely not be fully resolved until more interstellar objects are detected and studied. The shape of Oumuamua, as inferred from the large brightness variations, is another source of uncertainty and debate. The simplest interpretation of the brightness variations is that the object is highly elongated and rotating, with the brightness changing as different sides of the object are presented to the observer. If this interpretation is correct, then Oumuamua would be the most elongated known natural object in the solar system or beyond. However, there are other possible explanations for the brightness variations. One alternative is that the object is not uniformly reflective, and that the surface has bright and dark regions with different albedos. As the object rotates, the observer sees different mixtures of bright and dark surface, leading to brightness variations. This explanation does not require extreme elongation, but does require a non-uniform surface, which could result from compositional heterogeneity or from space weathering processes. Another alternative is that the object is in a complex rotational state, such as a tumbling rotation, where the object is rotating about multiple axes simultaneously. Tumbling rotations can produce complex light curves with variations that are not simply periodic, and in some cases, they can mimic the light curve of an elongated object. Distinguishing between these possibilities requires more detailed photometric observations, including observations at multiple wavelengths and from multiple viewing geometries, which were not possible for Oumuamua due to the limited observational window. The tumbling hypothesis is interesting because it could also explain the acceleration. If Oumuamua were tumbling, then any outgassing would produce a force that varies in direction as the object rotates, leading to a net acceleration that is different from the simple radial outgassing model. Modeling the dynamics of a tumbling object with outgassing is complex and requires detailed assumptions about the distribution of active areas on the surface and the rotation state of the object. Some researchers have performed such modeling and have shown that a tumbling ʻOumuamua with modest outgassing could produce an acceleration consistent with the observations. However, these models are not unique, and different assumptions about the shape, rotation, and activity of the object can lead to different predictions. The discovery of Borisov provided an opportunity to compare the properties of two interstellar objects and to begin to understand the diversity of the population. As mentioned earlier, Borisov was clearly a comet, with active outgassing and a composition similar to solar system comets, while ʻOumuamua appeared to be inactive and possibly asteroid-like. This difference suggests that interstellar objects come in a variety of types, just as solar system small bodies do. In the solar system, there is a continuum of objects ranging from rocky asteroids to icy comets, with many objects falling somewhere in between. The distinction between asteroids and comets is not always clear-cut, and there are objects that have properties of both, such as the so-called active asteroids, which display cometary activity but have orbits more typical of asteroids. It is likely that the interstellar population has a similar diversity, with some objects being predominantly rocky, some being predominantly icy, and some being intermediate. The relative abundance of different types of interstellar objects depends on the processes that eject objects from planetary systems and on the survival of those objects during their journey through interstellar space. Rocky objects, which form in the inner regions of planetary systems, might be less commonly ejected than icy objects, which form in the outer regions, because the outer regions typically contain more mass in the form of planetesimals. On the other hand, rocky objects are more durable and less subject to destruction by cosmic rays or collisions with interstellar gas and dust, so they might survive longer in interstellar space. Icy objects can lose their volatile ices through sublimation driven by cosmic ray heating, a process that could convert an initially icy comet into a rocky asteroid-like object over millions of years. This process, known as cosmic ray gardening or cosmic ray processing, involves the penetration of high-energy particles into the surface and interior of the object, where they deposit energy and break chemical bonds, leading to the release of gases and the alteration of the surface composition. The rate of this process depends on the flux of cosmic rays, the composition and structure of the object, and the timescales involved. For an object traveling through interstellar space for millions of years, cosmic ray processing could significantly alter its surface and even deplete its volatile inventory, turning a comet into a dark, inert body. The velocity distribution of interstellar objects provides information about their origins and the dynamical environment of the galaxy. The velocities of ʻOumuamua and Borisov, relative to the local standard of rest, were both consistent with typical stellar velocities in the solar neighborhood, suggesting that these objects were not recently accelerated by close encounters with other stars or by ejection from very young, dynamically active systems. The local standard of rest is defined as the average velocity of stars in the solar neighborhood, and objects that share this velocity are said to be in a relatively cold kinematic state, meaning they have not been significantly perturbed. If an object had been ejected from a planetary system during a recent close encounter between two stars, it might have a higher velocity, reflecting the additional energy imparted during the encounter. The fact that the observed interstellar objects have velocities consistent with the local standard of rest suggests that they have been wandering through the galaxy for a long time, long enough for their velocities to relax to the average velocity of the local stellar population. The direction from which interstellar objects approach the solar system is also of interest. If interstellar objects are distributed uniformly throughout the galaxy, then they should approach from all directions with roughly equal probability. However, if there are preferred directions, this could indicate that the objects are coming from a specific region of the galaxy or that their distribution is influenced by the structure of the galaxy, such as the spiral arms or the galactic disk. The directions from which ʻOumuamua and Borisov approached the solar system were different, and with only two objects, it is not possible to draw any strong conclusions about the directional distribution of the population. As more interstellar objects are detected, astronomers will be able to analyze the distribution of approach directions and look for any patterns or anisotropies that might provide clues about the galactic distribution of the population. The study of interstellar objects also raises questions about the fate of objects ejected from the solar system. Just as interstellar objects from other systems visit the solar system, objects ejected from the solar system will visit other systems. These objects carry with them a record of the conditions in the solar system at the time of their ejection, and in principle, they could be detected and studied by astronomers in those other systems, providing them with information about the solar system, just as interstellar objects provide us with information about other systems. The idea of sending a message or a probe attached to an object ejected from the solar system has been discussed as a form of interstellar communication or exploration, though the practicalities of such an endeavor are daunting. The objects ejected from the solar system are small, faint, and traveling at high velocities, making them difficult to detect even with advanced telescopes, and the timescales for such an object to reach another star are measured in hundreds of thousands or millions of years. The impact of interstellar objects on the understanding of planetary system formation is significant. Before the detection of interstellar objects, models of planetary system formation were based primarily on observations of the solar system and on observations of protoplanetary disks around young stars. These observations provide snapshots of planetary systems at different stages of evolution, but they do not provide direct information about the material that was ejected from those systems during their formation and evolution. Interstellar objects are the missing piece of this puzzle, representing the material that did not make it into planets or remain in bound orbits around the star. By studying the composition, structure, and properties of interstellar objects, astronomers can test the predictions of planetary system formation models and refine their understanding of the processes that shape planetary systems. One of the key predictions of planetary system formation models is that the composition of planetesimals should vary with distance from the central star, reflecting the temperature and pressure gradients in the protoplanetary disk. Close to the star, where temperatures are high, only refractory materials, such as silicates and metals, can condense, leading to the formation of rocky planetesimals. Farther from the star, beyond the snow line, temperatures are low enough for ices to condense, leading to the formation of icy planetesimals. The location of the snow line depends on the luminosity of the star and the opacity of the disk, and it moves inward over time as the disk cools. Models predict that the transition between rocky and icy planetesimals should be relatively sharp, with a narrow zone where both rock and ice are present. However, the actual composition of planetesimals can be more complex, with mixing between different regions of the disk due to dynamical processes such as turbulence, radial drift, and planetary migration. Interstellar objects, if they can be linked to specific formation regions in their parent disks, provide a way to test these models and to study the compositional gradients in protoplanetary disks. The composition of ʻOumuamua/Borisov, with its high abundance of carbon monoxide, suggests that it formed in a region of its parent disk where CO ice could condense and be retained. In the solar system, CO ice is thought to be abundant only beyond about 10 to 15 astronomical units from the Sun, in the outer regions of the Kuiper Belt and beyond. The presence of CO in ʻOumuamua/Borisov suggests that it formed in a similarly cold region of its parent disk, and that the thermal structure of that disk was not dramatically different from the thermal structure of the solar system's protoplanetary disk. This is an important result, because it suggests that the processes that govern the distribution of volatiles in protoplanetary disks are similar across different systems, even if the details of the planetary architectures differ. The size distribution of interstellar objects is another important observable that can be compared to models. In the solar system, the size distribution of asteroids and comets follows a power law, with the number of objects increasing as the size decreases. This power law reflects the collisional and accretional processes that shape this small body population over the history of the solar system. If interstellar objects follow a similar size distribution, it would suggest that the processes that produce these objects are similar across different systems. However, The size distribution of interstellar objects is currently poorly constrained because only a small number of objects have been detected, and all of them are relatively small, with sizes ranging from tens of meters to a few kilometers. Detecting larger interstellar objects would provide important information about the high mass and of the size distribution. But such objects are expected to be rare because larger objects are less easily ejected from planetary systems due to their higher masses. The thermal history of interstellar objects is another area of active research. As an object travels through interstellar space, it is heated by cosmic rays and by the interstellar radiation field, and it is cooled by thermal radiation. The balance between heating and cooling determines the object's temperature, which in turn affects its thermal evolution and the rate at which volatile ices are lost. The temperature of an interstellar object depends on its size, composition, and the properties of the interstellar medium through which it is traveling. For small objects, the temperature is typically very low, only a few tens of degrees above absolute zero, which allows volatile ices to be retained over long timescales. For larger objects, internal heat from radioactive decay or residual heat from formation can also contribute to the thermal budget, though these sources are less important for small objects. Understanding the thermal history of interstellar objects is important for interpreting their compositions and for predicting how they will behave when they enter the inner solar system and are heated by the sun. The collisional history of interstellar objects is also of interest. As objects travel through interstellar space, they are exposed to impact from interstellar dust grains, which are small particles of solid material, typically micrometers to millimeters in size, that are present in the interstellar medium. These impacts erode the surface of the object, creating a layer of processed material that may differ in composition and structure from the pristine interior. The rate of erosion depends on the density of dust in the interstellar medium and the velocity of the object. For typical interstellar velocities and dust densities, the erosion rate is very slow, on the order of a few centimeters per million years. So even after traveling for millions of years, the erosion would only remove a thin surface layer. However, this erosion could still affect the appearance and composition of the object's surface, and it could explain some of the reddish coloration observed in Oumuamua and other interstellar objects. The magnetic properties of interstellar objects are largely unexplored, but could provide additional information about their origins and evolution. Some meteorites, which are fragments of asteroids that have fallen to Earth, contain magnetic minerals that record the magnetic field of the solar nebula at the time of their formation. If interstellar objects also contain magnetic minerals, they could potentially record the magnetic field of their parent protoplanetary disk, providing a snapshot of the magnetic environment in that disk. However, measuring the magnetic properties of an interstellar object would require close-up observations, such as those that could be obtained by a spacecraft mission, and such measurements have not yet been made. The isotopic composition of interstellar objects is another potentially valuable diagnostic. Isotopes are variants of a chemical element that have different numbers of neutrons in their nuclei, and the relative abundances of different isotopes can vary depending on the conditions under which the material formed. In the solar system, isotopic compositions vary among different types of objects and are used to trace the origins of materials and the processes that affected them. For example, comets have different isotopic compositions of water compared to Earth's oceans, which has implications for the question of whether comets delivered water to Earth. If the isotopic compositions of interstellar objects could be measured, they could be compared to those of solar system objects and to theoretical predictions for other planetary systems. However, measuring isotopic compositions requires high-resolution spectroscopy or, ideally, laboratory analysis of returned samples, neither of which has been possible for interstellar objects detected so far. The rotation states of interstellar objects provide information about their dynamical history and their structural properties. The rotation of an object is affected by torques, which can arise from collisions, tidal interactions, or outgassing. In the absence of torques, an object's rotation state is conserved, but if torques are present, the rotation can speed up, slow down, or become chaotic. The rotation period of an object is related to its shape and internal structure. Elongated objects tend to rotate about their short axis, which is the axis of maximum moment of inertia, because this configuration is dynamically stable. If an object is in a tumbling state, rotating about an axis that is not a principal axis, the rotation can be complex and time-varying. The rotation state of ʻOumuamua, as inferred from the brightness variations, suggests a rotation period of approximately 7.3 hours, but the exact rotation state, whether it is a simple spin or a tumble, is uncertain. The rotation state of 2I/Borisov was less well characterized, partly because the presence of the coma made photometric observations more difficult, but the available data suggested a rotation period of a few hours. The study of interstellar objects benefits from comparisons to solar system objects, particularly those that are thought to be relatively pristine and unaltered since their formation. Comets from the Oort cloud are considered to be among the most pristine objects in the solar system because they have spent most of their history at large distances from the sun, where temperatures are very low and where solar heating and radiation are negligible. These comets are thought to preserve a record of the conditions in the outer solar system during the era of planet formation. The similarity between the composition of 2I/Borisov and that of Oort cloud comets suggests that the processes that formed and preserved these comets are similar across different planetary systems, which is a reassuring result for the field of comparative planetology. Transneptunian objects, which are small bodies located beyond the orbit of Neptune, are another population of interest for comparison to interstellar objects. These objects, which include Pluto, Eris, and thousands of smaller bodies, are thought to be remnants of the protoplanetary disk that did not accrete into planets. They are diverse in their physical and chemical properties, with some being predominantly rocky, some being predominantly icy, and some being covered in volatile ices, such as nitrogen or methane. The surfaces of many transneptunian objects are reddish, similar to the color of ʻOumuamua, and this reddish coloration is attributed to organic compounds that have been irradiated by cosmic rays and solar ultraviolet radiation. The study of transneptunian objects provides a baseline for understanding the properties of small bodies in the outer solar system, and this baseline can be used to interpret the properties of interstellar objects. Asteroids in the main belt, located between the orbits of Mars and Jupiter, are another comparison population. These objects are predominantly rocky and metallic, and they are thought to have formed in the inner solar system, inside the snow line. The diversity of asteroid types, as classified by their reflectance spectra, reflects variations in composition and thermal history. Some asteroids are rich in silicates, some are rich in carbonaceous material, and some are rich in metals. The reflectance spectra of asteroids can be compared to the spectra of interstellar objects to look for similarities or differences that might indicate common formation processes or distinct evolutionary histories. However, the spectra of ʻOumuamua were not detailed enough to allow a definitive classification, and the spectra of 2I/Borisov were dominated by gas emission, making comparison to asteroids difficult. The concept of the interstellar medium, the matter that exists in the space between stars, is important for understanding the environment through which interstellar objects travel. The interstellar medium is not empty, but rather consists of gas, primarily hydrogen and helium, along with trace amounts of heavier elements, and dust, which is composed of solid particles of silicates, carbon, and ices. The density of the interstellar medium is extremely low by terrestrial standards, typically only a few atoms per cubic centimeter, but over the vast distances of interstellar space, the cumulative effect of this tenuous material can be significant. Interstellar objects traveling through the medium experience drag from collisions with gas atoms and dust grains, which gradually slows them down. However, the drag force is very weak, and the effect on the object's velocity over the timescales of a few million years is negligible. More significant is the interaction of the object's surface with the interstellar radiation field and with cosmic rays, both of which can alter the surface chemistry and structure. The interstellar radiation field consists of photons at all wavelengths, from radio waves to gamma rays, with most of the energy in the ultraviolet and visible parts of the spectrum. These photons are produced by stars throughout the galaxy and by other energetic processes, such as supernovae and active galactic nuclei. When an interstellar object is exposed to this radiation, the photons interact with the molecules on the surface, breaking chemical bonds and driving photochemical reactions. Over long timescales, this process can alter the composition of the surface, creating a layer of irradiated material that differs from the pristine interior. The reddish color observed in many trans-Neptunian objects and in ʻOumuamua is thought to result from this kind of radiation processing, which produces complex organic molecules known as tholins. Tholins are a class of compounds formed by the irradiation of simple molecules such as methane and nitrogen, and they are characterized by their reddish color and their complex polymeric structure. Cosmic rays, which are high-energy particles, primarily protons and atomic nuclei, that travel through the galaxy at nearly the speed of light, also interact with the surfaces of interstellar objects. When a cosmic ray particle strikes the surface, it penetrates into the material, depositing energy and creating a cascade of secondary particles. This energy deposition can break chemical bonds, ionize atoms, and drive chemical reactions, leading to the formation of new molecules and the alteration of existing ones. Over millions of years, cosmic ray bombardment can significantly alter the surface composition of an interstellar object, creating a layer of processed material several meters thick. This processed layer may have different spectral properties than the pristine interior, and it may contain molecules that were not present when the object was first ejected from its parent system. The journey of an interstellar object through the galaxy is largely solitary. The distances between stars are so vast that the probability of a close encounter with another star or massive object is extremely low. The typical distance between stars in the solar neighborhood is a few light years, and at typical interstellar velocities of a few tens of kilometers per second, it takes tens of thousands of years for an object to travel 1 light year. Over the course of millions of years, an interstellar object will travel hundreds or thousands of light years, passing through different regions of the galaxy, but the chances of coming close enough to another star to be significantly perturbed are remote. Most interstellar objects will wander through the galaxy indefinitely, never again becoming bound to a star, unless they happen to pass close enough to a planetary system to be captured, which is also a rare event. Capture of an interstellar object into a bound orbit around a star requires that the object lose energy during its passage through the planetary system. This can happen through gravitational interactions with planets, which can act as a brake, slowing the object down enough that it becomes bound. However, such interactions are rare and require a precise alignment of trajectories. Alternatively, an object could lose energy through drag from gas in a protoplanetary disk if it happens to pass through a young stellar system where a disk is still present. The density of gas in a protoplanetary disk is much higher than in the interstellar medium, and the drag force can be sufficient to capture the object. Once captured, the object would become part of the planetary system, indistinguishable from objects that formed in that system, except possibly through differences in composition or isotopic ratios. It is possible that some objects currently in the solar system were originally captured from interstellar space, though identifying such objects is difficult because they have been dynamically mixed with the native population over the billions of years since the solar system formed. The role of interstellar objects in the broader context of galactic ecology is an emerging area of study. Galactic ecology refers to the study of how matter and energy flow through the galaxy, how different components of the galaxy interact, and how the galaxy evolves over time. Interstellar objects are one component of this system, representing a flux of solid material between stellar systems. This flux is small compared to the total mass of the galaxy, but it is not negligible, and over the history of the galaxy, a substantial amount of material has been redistributed through the ejection and wandering of interstellar objects. This redistribution could have implications for the chemical evolution of the galaxy, as objects ejected from one system can, in principle, deliver material to another system, potentially affecting the composition of planets forming in that system. However, The efficiency of this process is unclear, and it is debated whether the contribution of interstellar material to the formation of new planetary systems is significant. The theoretical framework for understanding interstellar objects draws on several areas of physics and astronomy, including celestial mechanics, thermodynamics, radiative transfer, surface chemistry, and collisional dynamics. Celestial mechanics provides the tools for calculating orbits and understanding the gravitational interactions that shape the trajectories of objects. Thermodynamics and radiative transfer are needed to model the thermal evolution of objects and to predict how their temperatures change as they move through different environments. Surface chemistry is important for understanding how the surfaces of objects are altered by radiation and chemical reactions. Collisional dynamics is needed to model the effects of impacts from dust grains and to understand the erosion and cratering of surfaces. Each of these areas contributes to a comprehensive understanding of interstellar objects, and progress in the field requires integrating insights from all of these disciplines. The models developed to understand interstellar objects are tested against observations, and discrepancies between models and observations drive the refinement of the models. For example, the non-gravitational acceleration of Oumuamua was not predicted by any model before it was detected, and its discovery prompted a flurry of theoretical work to explain it. Some of the proposed explanations, such as outgassing of molecular nitrogen, are testable through future observations of similar objects, while others, such as the light sail hypothesis, are more speculative and would require additional evidence to be taken seriously. The iterative process of observation, modeling, and theory development is central to the scientific method, and it is through this process that our understanding of interstellar objects will continue to advance. The technological developments that have enabled the detection and study of interstellar objects include advances in telescope design, detector technology, data processing, and computational modeling. Modern telescopes are equipped with large-format CCD or CMOS detectors that can capture images of vast regions of sky with high sensitivity. These detectors are far more efficient than the photographic plates used in earlier eras of astronomy, allowing fainter objects to be detected. Automated data processing pipelines analyze the images in near real time, identifying moving objects and flagging those with unusual properties for follow-up observations. Computational models, running on powerful computer clusters, simulate the dynamics of planetary systems and the galactic environment, providing predictions that can be tested against observations. All of these technologies work together to enable the detection and study of interstellar objects, and continued improvements in these technologies will lead to more detections and more detailed characterizations in the future. The societal and philosophical implications of discovering interstellar objects are subtle but worth considering. The realization that objects from other planetary systems regularly pass through our solar system challenges the notion of the solar system as an isolated entity and reinforces the idea that the solar system is part of a larger galactic community. It reminds us that the processes that shaped our solar system are not unique, and that similar processes are occurring throughout the galaxy. It also raises the tantalizing possibility that some interstellar objects might carry information about the planetary systems from which they were ejected, including potentially signs of life, though no such signs have been detected so far. The search for biosignatures on interstellar objects is a long-term goal of astrobiology, and while the chances of finding such signatures are low, the potential rewards are immense. The nomenclature and classification of interstellar objects follow conventions established by the International Astronomical Union, the organization responsible for naming celestial bodies and for establishing standards in astronomy. When an object is determined to have an interstellar origin, it is assigned a designation that begins with a number indicating its order of discovery, followed by the letter I for interstellar. Thus, Oumuamua is designated 1I. 2I/Borisov is designated 2I, and 3I/Atlas is provisionally designated 3I, pending confirmation of its interstellar nature. The object is also given a name, often chosen by the discoverer or by the team that confirmed its interstellar origin. The naming conventions are designed to be clear and unambiguous, allowing astronomers to refer to specific objects without confusion. The cataloging of interstellar objects is maintained by the Minor Planet Center, a service of the International Astronomical Union that collects and disseminates observations of asteroids, comets, and other small bodies. When an interstellar object is detected, its orbit is computed and published, and the observations are made available to the broader astronomical community. The Minor Planet Center also maintains a database of all known small bodies, including their orbital elements, physical properties, and observational history. This database is a valuable resource for researchers studying the dynamics and properties of small bodies, and it will become increasingly important as more interstellar objects are detected. The future observations of interstellar objects will likely focus on several key goals. One goal is to increase the detection rate, allowing the construction of a statistical sample that can be used to study the population as a whole. Another goal is to obtain more detailed characterizations of individual objects, including high-resolution spectroscopy, thermal infrared observations, and, if possible, resolved imaging. A third goal is to search for rare or unusual objects, such as very large interstellar objects, objects with extreme compositions, or objects that show signs of activity or other unusual phenomena. Each of these goals requires different observational strategies and different kinds of instruments, and progress will depend on the continued development of astronomical facilities and techniques. The Vera C. Rubin Observatory, with its large field of view and rapid survey cadence, is expected to revolutionize the study of transient and moving objects, including interstellar objects. The observatory's telescope has an aperture of 8.4 meters and a field of view of 9.6 square degrees, allowing it to image large areas of sky in a single exposure. The survey strategy calls for observing the entire visible sky every few nights, with each region of sky observed multiple times per night to detect transient events and moving objects. The data from a survey will be processed automatically, and alerts will be issued for objects that show unusual properties, such as hyperbolic orbits. The expected detection rate of interstellar objects by the Rubin Observatory is uncertain but could be as high as several per year, depending on the actual density of such objects in the solar neighborhood and their size distribution. Space-based telescopes, such as the James Webb Space Telescope, offer the possibility of more detailed observations of interstellar objects at infrared wavelengths. The infrared is particularly valuable for studying the thermal emission from objects and for detecting molecules that do not emit strongly in the visible part of the spectrum. The James Webb Space Telescope, with its large aperture and sensitive infrared detectors, is capable of detecting faint interstellar objects and obtaining high-quality spectra. However, the telescope's field of view is relatively small, and it is not well suited for survey work, so it would typically be used for follow-up observations of objects that have already been detected by ground-based surveys. The coordination between ground-based surveys and space-based follow-up observations will be an important aspect of future interstellar object studies. The concept of a dedicated mission to intercept and study an interstellar object has been explored in several studies. Such a mission would be extremely challenging, requiring rapid response capabilities and advanced propulsion systems. One proposed concept, known as Project Lyra, envisions a mission that could be launched on short notice when an interstellar object is detected, using a combination of gravitational assists from Jupiter and advanced propulsion to catch up with the object. The mission would carry instruments to image the object, measure its composition, and possibly collect samples. Another concept, known as the Bridge mission, proposes positioning a spacecraft in a distant orbit where it could intercept interstellar objects with less demanding propulsion requirements. Both of these concepts are currently in the early stages of study, and it is unclear whether they will be implemented, but they represent the kinds of ambitious missions that could provide transformative insights into the nature of interstellar objects. The study of interstellar objects also intersects with the study of exoplanets, planets that orbit stars other than the Sun. The same processes that eject interstellar objects from planetary systems also shape the architectures of exoplanetary systems, and understanding these processes is important for interpreting the observed properties of exoplanets. For example, The dynamical interactions that lead to the ejection of planetesimals can also cause planets to migrate inward or outward, altering the orbital structure of the system. The presence of a large population of ejected objects suggests that such dynamical interactions are common, and this has implications for the stability and long-term evolution of exoplanetary systems. Conversely, the detection and characterization of interstellar objects provide direct evidence for the ejection process and offer a way to test models of planetary system dynamics that are otherwise difficult to test. The chemical abundances in interstellar objects provide a window into the compositions of the protoplanetary disks from which they were ejected. The relative abundances of different elements and molecules reflect the temperature, pressure, and chemical conditions in the disk at the time the object formed. By measuring these abundances and comparing them to predictions from disk models, astronomers can learn about the physical conditions in disks and about the chemical processes that occur during planet formation. For example, the abundance of water relative to other ices, such as carbon dioxide or carbon monoxide, depends on the temperature profile of the disk and on the efficiency of various chemical reactions. If interstellar objects from different systems have different chemical abundances, this could indicate that the disks from which they came had different thermal structures or chemical environments. The dust in interstellar objects, if it can be studied in detail, provides another source of information. Dust grains in comets and asteroids are thought to be among the most primitive materials in the solar system, preserving a record of the conditions in the protoplanetary disk. The size distribution, composition, and structure of dust grains can be studied using a variety of techniques, including scattered light observations, thermal emission measurements, and, ideally, direct sampling and laboratory analysis. The dust in 2I/Borisov, as characterized by polarimetric and photometric observations, appear to be similar to the dust in solar system comets. But there were subtle differences that could reflect variations in the formation conditions or the processing history. More detailed studies of dust in future interstellar objects could reveal whether these differences are systematic or merely individual variations. The possibility of contamination of the solar system by interstellar objects is a topic of interest in planetary protection, the discipline concerned with preventing the contamination of celestial bodies by terrestrial life and vice versa. If an interstellar object were to impact a planet or moon in the solar system, it could deliver material from another planetary system, potentially including organic molecules or even, in principle, microbial life. The likelihood of such contamination is considered to be extremely low, given the rarity of impacts and the harsh conditions of interstellar space, which are lethal to most known forms of life. However, the possibility cannot be entirely ruled out, and it raises questions about how we should approach the study of interstellar objects and whether special precautions are needed when studying objects that might have biological significance. To date, no evidence of biological material has been found on any interstellar object, and the scientific consensus is that such contamination is unlikely. The energy budget of interstellar objects, the balance between the energy they receive and the energy they radiate, is an important factor in their thermal evolution. An object in interstellar space receives energy from the interstellar radiation field and from cosmic ray bombardment, and it loses energy through thermal radiation. The equilibrium temperature, the temperature at which the energy input equals the energy output, depends on the intensity of the radiation field, the object size and albedo, and the efficiency of thermal radiation. For typical interstellar conditions, the equilibrium temperature is only a few tens of degrees above absolute zero, which is cold enough to preserve volatile ices for very long timescales. When an interstellar object enters the inner solar system, it is heated by sunlight, and the temperature rises, potentially leading to the sublimation of ices and the onset of cometary activity. The rate at which the temperature rises depends on the object's thermal inertia, a property that describes how quickly the object's temperature responds to changes in heating. Objects with low thermal inertia heat up quickly, while objects with high thermal inertia heat up more slowly. The structural integrity of interstellar objects is another consideration. Objects that are weakly bound, such as porous aggregates or rubble piles, may be disrupted by tidal forces when they pass close to a star or planet, or by thermal stresses when they are rapidly heated. The tidal force is the difference in gravitational force across the object, and it increases as the object gets closer to a massive body. If the tidal force exceeds the object's tensile strength, the object can be pulled apart. The Roche limit is the distance within which tidal forces become strong enough to disrupt a fluid body, and for solid bodies, the critical distance depends on the material strength. Oumuamua passed within 0.25 astronomical units of the Sun, well outside the Roche limit for a solid rocky body, so tidal disruption is unlikely to have occurred. However, if Oumuamua were a loosely bound aggregate, it might have experienced some structural stress, though there is no observational evidence for disruption. Thermal stresses arise when different parts of an object are at different temperatures, leading to differential expansion or contraction. If the temperature gradients are large and the material is brittle, cracks can form and pieces of the object can break off. This process, known as thermal fracture or thermal cracking, is thought to occur on some comets and asteroids when they are heated by the sun. The fragments produced by thermal fracture can become small meteoroids that travel independently, and in some cases, they can produce meteor showers when Earth passes through the debris. Whether thermal fracture occurred on Oumuamua is unknown, but the rapid heating it experienced during its close approach to the sun could have produced thermal stresses. If fragments were produced, they would have traveled on slightly different trajectories and would now be scattered over a large region of space, making them extremely difficult to detect. The albedo of interstellar objects, the fraction of incident light that they reflect, is an important parameter for estimating their sizes. The brightness of an object depends on both its size and its albedo, and without independent information about one or the other, it is difficult to determine both. For Oumuamua, the albedo was estimated by assuming a range of plausible values and comparing the predicted brightness to the observed brightness. The resulting size estimates range from roughly 100 meters to several hundred meters, depending on the assumed albedo. For Borisov, the size of a nucleus was estimated using thermal emission measurements, which are less sensitive to the albedo, and the result was approximately 1 kilometer in diameter. The uncertainty in albedo is one of the major sources of uncertainty in size estimates for interstellar objects, and it highlights the value of multi-wavelength observations that can constrain the albedo independently. The color of interstellar objects, as measured by photometry at different wavelengths, provides information about their surface composition. The reddish color observed in Oumuamua and in many trans-Neptunian objects is thought to result from the presence of organic compounds that have been irradiated, as mentioned earlier. The exact shade of red and the spectral slope, the rate at which the reflectance changes with wavelength, can vary depending on the composition and the degree of irradiation. Some objects are neutral or gray in color, which could indicate a different composition, such as a surface dominated by silicates or carbon, or it could indicate that the surface has been refreshed by some process that removes the irradiated layer. The color of Borisov was more neutral than that of Oumuamua, which is consistent with the presence of fresh material exposed by cometary activity. The reflectance spectra of interstellar objects, if they can be obtained with sufficient quality, can reveal the presence of specific minerals or ices through absorption features at characteristic wavelengths. For example, water ice has strong absorption features in the near-infrared, and various silicate minerals have features in the mid-infrared. The detection of such features would provide direct evidence for the presence of these materials on the object surface. However, as mentioned earlier, the spectra of Oumuamua and Borisov were relatively featureless in the wavelengths where observations were made, either because the surfaces lacked strong absorbers or because the signal-to-noise ratio was insufficient to detect weak features. Future observations with more sensitive instruments, particularly in the infrared, may reveal spectral features that were not detected in the initial observations. The coma of Borisov, the cloud of gas and dust surrounding the nucleus, provided a wealth of information about the comet's activity and composition. The coma is produced by the sublimation of ices on the nucleus, which ejects gas and dust into space. The gas expands outward from the nucleus, forming a roughly spherical cloud, while the dust is carried along by the gas and also experiences radiation pressure from sunlight, which pushes it in the anti-sunward direction, forming a tail. The structure of the coma depends on the rotation of the nucleus, the distribution of active areas on the surface, and the production rates of different gas species. Observations of the coma can be used to infer the composition of the ices in the nucleus and to study the dynamics of gas and dust in the near-nucleus environment. The tail of ʻOumuamua/Borisov, which extended in the direction away from the Sun, was visible in images taken by ground-based and space-based telescopes. The tail is formed by dust particles that are pushed by radiation pressure and by gas that is ionized by solar ultraviolet radiation and then swept away by the solar wind. The shape and structure of the tail depend on the size distribution of the dust particles and on the interaction between the ionized gas and the solar wind. Observations of the tail can provide information about the dust production rate and the size of the dust particles, which are important for understanding the physical properties of the nucleus and the processes that release dust into space. The morphology of the coma and tail of ʻOumuamua/Borisov was found to be similar to that of solar system comets, with no obvious anomalies or unusual features. This suggests that the physical processes governing cometary activity are similar in different planetary systems, and that the structure and composition of cometary nuclei are not drastically different across different systems. However, subtle differences in the morphology, such as the presence of jets or spiral structures, could indicate differences in the rotation state or the distribution of active areas on the nucleus, and such differences would be interesting to study in more detail. The gas production rate of ʻOumuamua/Borisov, the rate at which gas is released from the nucleus, was estimated from spectroscopic observations and from models of the coma. The production rate varies with the comet's distance from the Sun, increasing as the comet gets closer and the solar heating becomes more intense. At perihelion, the production rate of ʻOumuamua/Borisov was estimated to be on the order of tens of kilograms per second for water and somewhat less for other gas species, such as carbon monoxide and carbon dioxide. These production rates are comparable to those of moderately active solar system comets, indicating that ʻOumuamua/Borisov was not unusually active or inactive compared to solar system comets of similar size. The dust production rate, the rate at which dust is released from the nucleus, is more difficult to measure than the gas production rate because dust does not emit light but rather reflects sunlight. The brightness of the dust in the coma and tail depends on the dust production rate, the size distribution of the dust particles, and the scattering properties of the dust. By modeling the brightness of the coma and tail and comparing the model predictions to the observations, astronomers can estimate the dust production rate and the properties of the dust. For ʻOumuamua/Borisov, the dust production rate was estimated to be on the order of tens to hundreds of kilograms per second, similar to the gas production rate, though the uncertainty is larger due to the difficulty of modeling the dust scattering. The lifetime of interstellar objects in interstellar space is effectively infinite, barring a close encounter with a star or another massive object. Once an object is ejected from its parent system and reaches interstellar space, it will continue to travel at nearly constant velocity, following a straight-line trajectory through the galaxy for as long as the galaxy exists. The timescale for a close encounter with another star is tens of billions of years, far longer than the current age of the galaxy, so most interstellar objects will never experience such an encounter. They will simply wander through the galaxy indefinitely, occasionally passing through planetary systems like ours, but spending the vast majority of their time in the empty space between stars. The galactic orbit of the Sun and of interstellar objects that happen to pass through the solar system is governed by the gravitational potential of the Milky Way galaxy. The galaxy is not a static structure, but rather a dynamic system in which stars, gas, and dark matter move under the influence of gravity. The Sun orbits the galactic center with a period of approximately 225 million years, traveling at a velocity of approximately 220 kilometers per second relative to the galactic center. Interstellar objects that pass through the solar system have their own galactic orbits, which may be similar to the Sun's orbit or quite different, depending on their velocities and their locations in the galaxy. The diversity of galactic orbits among interstellar objects contributes to the diversity of velocities and approach directions observed when they enter the solar system. The spiral structure of the Milky Way, the pattern of spiral arms that can be seen in images of other galaxies and that is inferred to exist in the Milky Way, plays a role in the distribution of stars and interstellar objects in the galaxy. Spiral arms are regions of enhanced density where stars and gas are concentrated, and they are sites of active star formation. Objects that pass through spiral arms may experience slightly different conditions, such as higher densities of interstellar gas or more frequent encounters with molecular clouds, though these effects are generally minor. The Sun is currently located between two spiral arms, in a region known as the local arm or the Orion spur, and it moves in and out of spiral arms over the course of its galactic orbit. The passage through spiral arms does not have a dramatic effect on the solar system or on interstellar objects passing through the solar system, but it does contribute to the overall dynamical environment of the galaxy. The dark matter halo of the Milky Way, the large-scale distribution of dark matter that surrounds the galaxy and that dominates the galaxy's gravitational potential, also plays a role in the dynamics of interstellar objects. Dark matter does not emit light and is detected only through its gravitational effects, but is thought to make up the majority of the mass of the galaxy. The gravitational potential created by the dark matter halo determines the overall structure of the galaxy and the orbits of stars and other objects within it. Interstellar objects, like stars, move within this potential, and their trajectories are shaped by the distribution of dark matter. However, on the scales relevant to the motion of interstellar objects through the solar system, the effects of dark matter are negligible, and the primary gravitational influence is that of the Sun and the planets. The metallicity of interstellar objects, the abundance of elements heavier than hydrogen and helium, provides information about the stellar populations from which they originated. In astronomy, elements heavier than hydrogen and helium are referred to as metals, even though many of them are not metals in the chemical sense. The metallicity of a star or planetary system is determined by the composition of the gas cloud from which it formed, and this composition is shaped by the history of star formation and stellar evolution in the galaxy. The first generation of stars, which formed from the primordial gas left over from the Big Bang, had very low metallicity because that gas contained almost no heavy elements. Subsequent generations of stars formed from gas that had been enriched by the nuclear fusion in earlier stars and by supernova explosions had higher metallicities. The Sun is a relatively high metallicity star, reflecting the fact that it formed relatively recently in the history of the galaxy from gas that had been enriched by many generations of stars. Interstellar objects that formed in planetary systems with different metallicities might have different compositions, and measuring the metallicity of interstellar objects, if it can be done, could provide information about the age and history of their parent systems. The habitability of planetary systems and the potential for life in the universe are topics of intense interest in astrobiology, and the study of interstellar objects has some connection to these topics. If interstellar objects can transport organic molecules between planetary systems, then they could play a role in the distribution of the building blocks of life throughout the galaxy. However, the harsh conditions of interstellar space, including intense radiation, extreme cold, and the near-perfect vacuum, make it unlikely that complex organic molecules, or, especially, living organisms could survive the journey. Simple organic molecules, such as amino acids, are more robust and might survive if they are protected within the interior of a larger object, but even this is uncertain. The detection of organic molecules on interstellar objects would be an important step in assessing the viability of panspermia, but so far, no such detection has been made. The Fermi paradox, the apparent contradiction between the high probability of the existence of extraterrestrial civilizations and a lack of evidence for such civilizations, is sometimes invoked in discussions of interstellar objects, particularly in the context of the light sail hypothesis for ʻOumuamua. If advanced civilizations are common in the galaxy, And if they have developed interstellar travel technology, then we might expect to see evidence of their presence in the form of artifacts or probes. Interstellar objects, if they were artificial, could be such artifacts. However, as mentioned earlier, there is no convincing evidence that ʻOumuamua or any other detected interstellar object is artificial, and the scientific consensus is that they are natural objects. The Fermi paradox remains unresolved, and the search for extraterrestrial intelligence continues through other means, such as the search for radio signals or optical signals from distant civilizations. The public interest in interstellar objects has been significant, reflecting a broader fascination with the possibility of contact with extraterrestrial life and with the exploration of the unknown. The discovery of ʻOumuamua generated widespread media coverage, and the debate over its nature and origin captivated the public imagination. The name ʻOumuamua itself, with its evocative meaning and its connection to Hawaiian culture, contributed to the public interest. The discovery of Borisov, while less dramatic than that of ʻOumuamua because it was more clearly a normal comet, also received significant attention. The public interest in these objects reflects a recognition of their significance as visitors from beyond the solar system, and as windows into the processes that shape planetary systems throughout the galaxy. The communication of scientific findings about interstellar objects to the public presents challenges. The science involved is complex, involving concepts from celestial mechanics, spectroscopy, thermodynamics, and other areas of physics and astronomy that may not be familiar to the general public. The uncertainties in the data and the debates among scientists about the interpretation of the data can be difficult to convey without creating the impression of confusion or disagreement. The media coverage of interstellar objects has sometimes emphasized the more speculative or sensational aspects of the findings, such as the possibility that ʻOumuamua might be artificial, at the expense of the more mundane but scientifically important aspects. Effective science communication requires balancing the need to convey the excitement and significance of the discoveries with the need to accurately represent the state of scientific knowledge and the uncertainties involved. The interdisciplinary nature of interstellar object studies brings together researchers from many different fields, including planetary science, astronomy, astrophysics, chemistry, and even biology. Each of these fields contributes a different perspective and a different set of tools to the study of interstellar objects. Planetary scientists bring expertise in the physical and chemical properties of small bodies and in the processes that shape their surfaces and interiors. Astronomers bring expertise in observational techniques and in the analysis of light from distant objects. Astrophysicists bring expertise in the dynamics of stars and galaxies and in the large-scale structure of the universe. Chemists bring expertise in the composition and reactivity of molecules and in the chemical processes that occur in space. Biologists, though their contribution is more speculative at present, bring expertise in the requirements for life and in the potential for life to exist in extreme environments. The collaboration among researchers from these different fields is essential for making progress in understanding interstellar objects. The long-term vision for interstellar object studies includes not only the detection and characterization of more objects, but also the development of a comprehensive theoretical framework that can explain their origins, properties, and evolution. This framework would integrate models of planetary system formation, dynamical evolution, surface chemistry, thermal history, and galactic ecology, providing a unified picture of how interstellar objects fit into the broader context of the galaxy. The framework would also make predictions that can be tested through future observations, guiding the design of observational campaigns and the development of new instruments. As more data are collected and as models are refined, the understanding of interstellar objects will become more complete, and the field will transition from a state of discovery and exploration to a more mature state, where the focus is on understanding the underlying physical processes and on using interstellar objects as tools for studying the galaxy. The comparison between interstellar objects and meteorites, fragments of asteroids or comets that have fallen to Earth, is instructive. Meteorites provide the opportunity for detailed laboratory analysis, including measurements of composition, isotopic ratios, mineral structure, and age. This kind of detailed analysis is not currently possible for interstellar objects because we have not yet returned a sample to Earth. However, if a sample of an interstellar object could be obtained, it would provide a wealth of information that cannot be obtained through remote observations alone. The study of meteorites has revolutionized our understanding of the solar system and of the processes that occurred during its formation, and a similar revolution could occur in the study of other planetary systems if samples of interstellar objects could be analyzed in the laboratory. The search for meteorites of interstellar origin on Earth has been proposed as a way to study interstellar objects without the need for a space mission. If an interstellar object were to impact Earth, fragments of it might survive the atmospheric entry and be recovered as meteorites. These meteorites would have unusual compositions or isotopic ratios that would distinguish them from solar system meteorites. However, identifying such meteorites is extremely challenging because the vast majority of meteorites are from solar system sources, and the signatures of interstellar origin are subtle and easily obscured by terrestrial contamination or by the effects of atmospheric entry. Some researchers have searched for interstellar meteorites by looking for objects with unusual properties or by analyzing the trajectories of meteors to identify those that have hyperbolic orbits, but no confirmed interstellar meteorites have been found to date. The velocity of interstellar objects relative to the Sun is a key observable that provides information about their origins and their motion through the galaxy. The velocity at infinity, the velocity that the object would have far from the Sun's gravitational influence, is calculated from the orbital elements and is typically in the range of 20 to 40 kilometers per second for objects detected so far. This velocity is comparable to the velocity dispersion of stars in the solar neighborhood, suggesting that interstellar objects share the general motion of the local stellar population. However, individual objects can have velocities that are higher or lower than the average, depending on their specific galactic orbits and on any perturbations they may have experienced. The distribution of velocities among a large sample of interstellar objects would provide information about the dynamical state of the galaxy and about the processes that eject objects from planetary systems. The concept of the solar apex, the direction in the sky toward which the Sun is moving relative to the local standard of rest, is relevant to the study of interstellar objects. The solar apex is located in the constellation Hercules, and the Sun is moving toward this direction at a velocity of approximately 20 kilometers per second relative to the local standard of rest. Interstellar objects that are stationary relative to the local standard of rest would appear to approach the solar system from the direction of the solar apex. However, because interstellar objects have their own galactic velocities, which may differ from the local standard of rest, the distribution of approach directions is not simply concentrated toward the solar apex, but is spread over a range of directions. The analysis of approach directions for a large sample of interstellar objects could reveal patterns that reflect the structure and motion of the local stellar population. The eccentricity of the orbits of interstellar objects, the parameter that describes how elongated the orbit is a key indicator of their interstellar origin. For objects on bound orbits around the Sun, the eccentricity is less than 1, and the orbit is an ellipse. For objects on unbound orbits, the eccentricity is greater than or equal to 1, and the orbit is a parabola or hyperbola. An eccentricity of exactly 1 corresponds to a parabola, which is the boundary between bound and unbound orbits. Objects with eccentricities only slightly greater than 1 have orbits that are only weakly unbound, meaning they're moving only slightly faster than the escape velocity. Objects with higher eccentricities are more strongly unbound and are moving at higher velocities. The eccentricities of ʻOumuamua and 2I/Borisov were both significantly greater than 1, confirming their interstellar origin, while the eccentricity of 3I/Atlas was closer to 1, leading to some uncertainty about whether it is truly interstellar. The inclination of the orbits of interstellar objects, the angle between the orbital plane and the plane of the solar system, provides information about the direction from which they approached. Objects with low inclinations approach the solar system from directions close to the plane of the solar system, while objects with high inclinations approach from directions far from the plane. The inclinations of ʻOumuamua and Borisov were both relatively high, indicating that they approached from above or below the plane of the solar system. This is not surprising because interstellar objects can approach from any direction, and there is no reason to expect them to be concentrated in the plane of the solar system. The argument of perihelion and the longitude of the ascending node are additional orbital elements that describe the orientation of the orbit in space. The argument of perihelion specifies the location of the closest approach to the Sun within the orbital plane, while the longitude of the ascending node specifies the orientation of the orbital plane relative to a reference direction. Together, these elements fully describe the three-dimensional shape and orientation of the orbit. For interstellar objects, these elements are determined from astrometric observations and are used to reconstruct the trajectory of the object through the solar system. The study of interstellar objects is still in its infancy, with only a handful of confirmed or suspected objects detected so far. Each new detection adds to the small but growing body of knowledge about these objects and provides new opportunities to test theoretical models and to refine observational techniques. The pace of discovery is expected to accelerate in the coming years as more powerful survey telescopes come online and as the astronomical community becomes more adept at recognizing and characterizing interstellar objects. The field is poised for rapid growth, and the next decade is likely to see a significant increase in the number of known interstellar objects and in the depth of our understanding of their properties and origins. The connection between interstellar objects and the broader field of small body studies is strong. Many of the techniques and concepts developed for studying asteroids and comets in the solar system are directly applicable to the study of interstellar objects, and vice versa. The study of interstellar objects enriches our understanding of solar system small bodies by providing a comparative context, and the study of solar system small bodies provides a foundation for interpreting the properties of interstellar objects. This synergy between the two fields is beneficial for both, and it highlights the value of a broad, integrative approach to planetary science. The role of citizen scientists in the discovery and study of interstellar objects should not be overlooked. Amateur astronomers, equipped with increasingly sophisticated telescopes and cameras, have made significant contributions to the field of small body studies, including the discovery of comets and asteroids. The discovery of Borisov by an amateur astronomer is a testament to the value of these contributions. Citizen science projects, which engage members of the public in data analysis and discovery, have also played a role in identifying transient and moving objects in large astronomical datasets. The continued involvement of citizen scientists in interstellar object studies will be important for maximizing the scientific return from future surveys. The uncertainties in the properties of interstellar objects, arising from the limited quality and quantity of observational data, are a recurring theme in the study of these objects. Every measurement has associated uncertainties, and these uncertainties propagate through the analysis, affecting the derived properties such as size, shape, composition, and trajectory. Reducing these uncertainties requires better data, obtained with more sensitive instruments and with more extensive observational coverage. The challenge of obtaining such data for fast-moving, faint objects is significant, and it requires careful planning and coordination among observers. The development of automated systems for rapid follow-up observations, triggered by the detection of new interstellar objects, will be important for improving the quality of the data and reducing the uncertainties. The concept of the cross-section for detection, the effective area in space within which an interstellar object can be detected by a given survey, is important for estimating the population density of interstellar objects. The cross-section depends on the sensitivity of the survey, the size and brightness of the objects, and the geometry of the solar system. Surveys that can detect fainter objects have larger cross-sections and are more likely to detect interstellar objects. The cross-section also depends on the distance from the Sun at which the object is observed, with objects detected closer to the Sun being brighter and more easily detected. By calculating the cross-section for a given survey and comparing it to the number of detections, astronomers can estimate the number density of interstellar objects in the solar neighborhood. The relationship between the number density of interstellar objects and the rate of ejection from planetary systems is governed by the dynamics of the galaxy. The number density is determined by the rate at which objects are ejected into interstellar space and by the rate at which they are removed from the population, either through collisions, capture by stars, or other processes. In steady state, the rate of ejection equals the rate of removal, and the number density remains constant. If the ejection rate is higher, the number density increases over time, and if the ejection rate is lower, the number density decreases. The observed number density provides a constraint on the ejection rate, averaged over the history of the galaxy, and this constraint can be compared to predictions from planetary system formation models. The exploration of interstellar objects represents one of the frontiers of astronomy, a frontier that is just beginning to be explored. The objects detected so far are the first glimpses of a vast population that has been traveling through the galaxy for billions of years, carrying with them information about the planetary systems from which they came. Each detection is an opportunity to learn something new, to test theoretical predictions, and to refine our understanding of the processes that shape planetary systems and the galaxy as a whole. The study of interstellar objects is a long-term endeavor, one that will continue for decades or centuries as more objects are detected and as observational techniques continue to improve. The narrative of interstellar objects is one of deep time and vast distances, of objects that were ejected from their parent systems millions or billions of years ago and that have been traveling through the cold, dark expanse of interstellar space ever since. It is a narrative that connects the solar system to the broader galaxy, reminding us that the solar system is not isolated, but is part of a dynamic, interconnected system. It is a narrative that invites us to look beyond our immediate surroundings and to consider the processes that occur on galactic scales, shaping the distribution of matter and the evolution of planetary systems. It is a narrative that, for now, remains incomplete, with many questions unanswered and many mysteries yet to be solved. But it is a narrative that continues to unfold, with each new observation adding another piece to the puzzle, and with the promise of future discoveries that will deepen our understanding and expand our perspective. The silence of space, the vast emptiness through which these objects travel, is profound. There is no sound, no air, no warmth except the faint glow of distant stars. There is only motion, the inexorable drift of objects through the void, following trajectories determined by the gravitational pull of the galaxy and by the chance events that set them on their journeys. In this silence, the interstellar objects continue their paths, unaware of the telescopes that briefly capture their light, unaware of the scientists who puzzle over their properties, unaware of the significance that humanity assigns to their passage. They are messengers, but they carry no conscious message. They are visitors, but they do not visit with intent. They simply are, and in their being, they reveal something of the universe in which we find ourselves, a universe vast and ancient and filled with wonders that we are only beginning to comprehend.